All right, recording is rolling. It is Monday, April 21st. We have 25 days until the exam. So last week I was taking a few days to do circuits and Kirchhoff tables with you guys. So we never quite got to this page. So this is going to be our focus today. We're going to do a bit more circuits, so Ohm's law, Joule's law thing. Right. I do need to get you guys rolling on practice exam 3. So we'll do that later this week, possibly tomorrow. We'll see how far we got on this page. Either tomorrow or Wednesday, we'll start our practice exam 3. All right, so you guys know the exams in two halves. There's a free response half and a multiple choice half. All right, here, I need to poll you guys how you want to do the multiple choice. All right, do you want to do the multiple choice in class? And the advantage then could be that we would do this over 2 days and you get like a good feeling for exactly how much time you have to do it and feel the stress, and it could be realistic. Right? Or instead, I can assign you guys to do that for weekend homework. Like I could open this up like later today and give you guys like a week to do this. Right? And the advantage of that would be we could have 2 extra days to do other types of review in class. Right? Now the pre-response questions I do want to have you guys do in class for 2 days. I'll have you get the desks in rows. All right, so that'll simulate something pretty close to reality. All right, so let's see. All right, you guys ready to vote on this? Ready to vote on this? All right, so the multiple choice questions. Do you want to do those in class for 2 days, or just do this for homework and we can take the extra 2 days and do extra study here? All right, who wants to do the multiple choice for practice exam 3 in class? Who says in class? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Who wants to do the homework? I can open up. How do you guys do it for homework? Got 1, 2, 3, 4, 5, 6, 6. All right, 12, 6. All right, so plan that. So we'll do a couple days in class for FRQ and a couple days in class for MCQ, and of course we'll debrief the whole thing. But yeah, we got time to do that, so we'll do that. All right, you guys good with that? So plan on that. Okay. You guys probably saw there was some pretty big science news over the last few days. So here, I hit this real fast. How many of you guys saw this? James Webb Space Telescope picked up a ring of dimethyl sulfide from this exoplanet. You guys saw that story? Probably so. Yeah. All right. So if you did, then I probably don't know any more than you do, but it goes like this. Um, so lots of stars have planets orbiting them. I mean, that was an open question just a generation ago. Nobody knew quite sure, but we've been set up all these space probes and telescopes, and look at these stars out there. Now, the way that we know that a star has an exoplanet in front of it is because you can watch how much light is coming from it, and the light will dim a little bit. Now, depending on how much light dims and for how long, you can get a pretty good estimate of like the diameter of a planet and also how far away it is from its parent star, right? Because when it's passing in front of the star, then the light dims a little bit, right? Now, of course, we would only notice this if it just happens to be that the orbit of the planet is also in the same plane to line up with Earth, right? Like if it was orbiting like this, there you go, there are lots of solar systems probably doing that too. We would just never have the opportunity to see a planet at all. Okay, so we see this exoplanet. Now, if this exoplanet has an atmosphere, then any starlight that's passing through that atmosphere, we can see a signature of the chemicals from that atmosphere using spectrometers. That's spectrometry. And there's this particular chemical that was found to be in the atmosphere of this planet, dimethyl sulfide, which, as far as we know, we've only ever seen or no way for that to be created is from organic life, right? So this is possibly detection of life outside our solar system, right? Now, of course, scientists try to go back and get a lot more ratings from this planet, say, are we really seeing what we think we're seeing? And then have a whole speculation of, well, is it possible that this might have been created through some other process that maybe we don't understand yet, right? So anyway, a little bit of an open question right now, but a pretty big story. So there you go. All right, let's look at these circuits. Are you guys ready for circuits? All right, so on one side is Kirchhoff tables. We'll save those for a little bit later today. All right, I got some classic lookup circuits on this side. Now, just to brush you guys up, since you guys only see this for a couple of days from last week, we're looking at scenarios like this, where we got some voltage source For example, a battery could be 9 volts, right? Think of this like a pump, right? Some resistor like this Christmas light right here, and then make a complete circuit, and you're going to get current to flow, right? And that's what capital I is, and we're going to measure current in amps. There you go. Here's Ohm's law that relates to those three variables. So more voltage, more current, more resistance, less current. Boom, there you go. Okay. There's also the question, what's the power in watts, which you guys know is a rate of energy transfer. It's a rate the batteries being drained. You go power is current times voltage, or current squared times resistance, or voltage squared by resistance. They'll all get to there. Okay. Now here's what we're headed towards today. We're about to get to this. Is if you have resistors in series, one after another, that could be like this. Okay. Then the total resistance from the point of view of the battery, every time you add a resistor in series, it increases the resistance. You just very simply add them together. Okay. But if you have them like rungs of a ladder, we'll call that in parallel, the total resistance actually decreases. And the math is the same as teamwork. So my classic example is a team of friends paint a fence. If it's one guy paint a fence, how much time does it take? Maybe a long time. But if he gets his friends to paint with them, it's less and less time. Replace time with resistance and ohms, and there you go. So that could look like this. Here's 3 resistors in parallel. Okay, so like that. Right? Oh, and look, they're all really bright too. Right. Right, now that's the total resistance from the point of view of the battery. Okay, so that's the main ones. Now, if you're digging around inside a circuit, you want to figure out exactly how does current flow and exactly how does voltage drop across each resistor. Right, I have a basic series setup, a basic parallel setup. Here's Kirchhoff's rule. Kirchhoff has these 2 rules: this loop rule right here, this junction rule right here, and all these other rules also fall out of those. Okay. I got some waterfall models for you guys, which we're headed towards. Right? So if they're all in series, then the current is the same everywhere. Okay, and the voltage drops a little bit at a time, so the voltages add up to the voltage from the battery. Okay. Okay, and here's some example numbers. We'll fill out some tables like this later today. If they're all in parallel, then the voltage drop is the same across everyone. So if this is a 9-volt battery, then every one of these gets 9 volts. Okay? But the current splits. So if it was like 30 amps left, maybe it splits like 10 amps, 8 amps, and 12 amps, depending on what the resistors are. Okay, so give you guys an example right there. Some numerical example. Okay. And of course, you gotta have a hybrid setup, right? Well, like, okay, well, I've got some series with some parallel, depending on which one, like these 2 are parallel with each other, which is series with this guy, parallel with this guy. Okay, so that, right? And then you've got a real complex looking one. Yeah, so a little fancier looking whole table of potential odds. Right. Okay. Now for all these tables, I would have to give you all the resistors and the voltage of the battery, right, which I kind of shaded in yellow here. And then once you have those locked in place, then all these other numbers become determinable. All right, so quick recap, some stuff you guys saw yesterday. Let's solve some of these. Okay, so here guys, just do the ones I'm doing with you guys. Here, I should prop this up. Let's see if I can prop this up a little bit better. Okay, blink. It's a little easier to see, maybe. Okay. Well, okay. My numbers are different than your numbers, but we all have the same geometry circuits. All right, so the very first one is very simply a voltage source and a resistor. And it tells you what the resistor is. Mine says 1 ohm, therefore the total resistance would be 1 ohm. Okay, so guys, the answer to number 1 is just whatever resistor is on there. You guys got that? You guys got that? Okay. Now, number 2, if you trace the current around, go from the battery and trace around the circuit, guess you have to go through both of the resistors sequentially, one after another. That means they're in what? Series or parallel? Series. So can you very simply add them up? Yeah. Now mine are 3 ohms and 4 ohms. So on number 2, I would say resistance total is 3 ohms plus 4 ohms. That makes 7 ohms from the point of view of the battery. So the answer is 7 ohms. Right. Now yours, you just add them together. Okay, got that? Okay. Hey, number 3. All 3 of those are all in what with each other? Series. Yeah, so you can just add them together again, right? Okay, so you can say resistance total. Now mine goes 7 ohms, 8 ohms, and 9 ohms. So what was that 24, I think? 24 ohms. That's a boom, 24. All right, you guys got number 1, 2, and 3? You guys good? Okay, now number 4. You guys see if you're tracing the current around, it hits this junction, and then the current is forced to split. That means those resistors are in what with each other? Parallel. So can you add them together, or do you treat it like 2 guys painting a fence? You guys painting a fence, right? Now you could use the reciprocal method. I'm going to use the product over sum method on this one. So I'm going to say the total resistance is product over sum. Now mine are 7 and 8. So I'll go 7 times 8 divided by, and then in parentheses 7 plus 8. This would be some number of ohms. So is that 56 over 15? Okay, calculator time. What does that fraction come out to? Okay. So my calculator's telling me this decimal right here. I think that looks about right. Do I see an answer choice? Yeah, I see an answer choice right there. Okay. Or is everybody out there also getting an answer choice on number 4? Let's do that. Did everybody do number 4, product over sum? Got an answer. Everybody good? Ready for the next one? Okay. Number 5. Ooh, guys, those 3 resistors are all in love with each other. Parallel. Okay. This one I'll go ahead and do the fraction method for just to change it up a little bit. I don't normally default the product over sum, but okay, let's try the fraction method. So you can say 1 over the total resistance of 3 in parallel. Okay. Now mine go 1 over 8, 1 over 10, and 1 over 12, because my resistors are 8, 10, and 12. Okay. So I'll let the calculator handle this. I'm not going to worry about trying to find common denominator, or just let the calculator do it. That fraction plus that fraction plus that fraction. Okay, that's something. That's 1 over the answer is equal to this crazy looking decimal. And that'd be 1 over ohms. Okay. All right. So guys, how do I find the answer from here? What's the last step? Yeah, take the reciprocal. Now there's a reciprocal key. It's right above the 7. You can hit that if you want, or you can go 1 over the answer, however you do it. Right. It's a couple ways to get there. All right. So mine is saying this many ohms. Okay. Now, does that look reasonable? Well, if it was 8, 10, and 12 hours to paint a fence, 3-man team, could they knock out the job in about 3.5 hours? Yeah, I think that looks about right. All right, so is that an answer choice? Yeah, that is right here. Okay. Are you guys also getting an answer choice on number 5? Very good. Okay. So is everybody good on 1 through 5 so far? Everybody's good 1 through 5? Okay, knocking these out. Okay. All right. Now I'm seeing some hybrid setups for the next period. All right, so from here on out, the rest of these are going to be processes. Okay, processes. Okay. We're going to draw some equivalent circuits. Okay. So starting with number 6, there's a certain set of rules to these processes, and it goes like this: find your voltage source, which is on the left side. Put it always on the left side. Okay. Okay. Fly over to the complete opposite side of the circuit, as far away as you can get from the voltage source. It's going to be important from here on out. Okay. And then work your way back towards the voltage source and find equivalent circuits along the way. So there are 3 resistors on number 6, but the first 2 you run into, again, far away from the circuit, are these 2 here. You guys, these 2 in isolation are in what with each other? Series or parallel? Parallel. So what I'm going to do is draw an equivalent circuit. Here, actually, draw the original circuit first. Okay. So I have this one looks like this many ohms. This one is this many ohms. And this one is this many. Okay, so there's my original circuit. Yeah, these 2 are in parallel, you guys said. So let's do product over sum. So that could be product over sum, number of ohms. So 80 on 18. What does that come out to? Okay. That's like this many ohms right here. Okay. Okay. It's as if those 2 resistors are collectively acting as a single resistor of that many ohms. Does that make sense? Okay. So now I'm going to redraw the circuit. And it's a pretty simple one right here. Okay. So, okay. All right, so see, I haven't touched this guy at all, so I'm just going to redraw him. Right. But these 2 are collectively acting like a single resistor. So I'm going to, whoops, do that. This many on point right there. Okay. All right, you guys did about the same thing with your own numbers. Okay. All right. And now moving back towards the source, these resistors are now what with each other? Series or parallel? Series. Yeah. So can I just add them together? Yeah. So now the total resistance for the whole circuit, the answer to the question, take this resistor, add these collective resistors, solve that. I think it's going to give me, what, this many ohms right here? Does that look about right? About like that? All right. Okay. Let me see. Is that an answer choice? Point. Yep. Right there. How you guys doing? You guys all right? We're at?
I don't see it. I see 16.8, not 16.4.
Oh, okay. Well, my numbers are different than your numbers. Okay. Okay. It's a. All right. So my resistors are 8, 10, and 12 ohms, and what yours are different numbers.
4, 12.
4, 4, 12. Okay. So take 4 and 12, do product over sum, write that down, and then add the other one to it, and then that'll get you the. Okay. All right. All right. Let's do number 7. Number 7. So here, draw what I got. Okay. So it looks a little different. I did wire these up for you guys last week too. I meant to mention this. Here, maybe see if I can pop this together real fast. Yeah, I have it right here. Have it right here. Where's my battery? Okay. Okay. So guys, does this look like this where point? Okay. You guys see how I have one that's really bright and two that are relatively dim? You guys see that? Okay. Because the bright one, doesn't the bright one get all the voltage across it? Like if this is 9 volts right here, doesn't this get the full 9 volts? It just goes like that. Full 9 volts. Okay. Versus these two, when it's stepped down, like maybe 4.5 volts and 4.5 volts. Or maybe it steps down like 3 volts and 6 volts. So they add up to 9. Right. Okay. We got. All right, throw some numbers. So this looks like this many ohms. This is this many ohms. This is this many ohms. Okay. Okay, so remember the rules is I find my voltage source, I fly over to the opposite side of the circuit. I'm going to work my way back towards the source. Okay. And these two, like the first two to start with, are in love with each other, series or parallel. Series. Yeah, series. And you know that because whatever current happens to go through one also has to go through the other one. Okay. Okay. Now that's not to say that's all the current leaving the battery, but we haven't got to that part yet because we know it's going to split at this point. But we're not even there yet. Okay. These two are in series. So can I very simply add those together? Yeah, that many ohms plus that many ohms is that many ohms. Okay. Then redraw the circuit. Draw an equivalent circuit. So redraw circuit right here. Okay, so I still got this resistor here, haven't touched yet. But these two are collectively acting as a single resistor with that many ohms. Okay, here's good. Okay, and your numbers are working out so far? Working out. Okay. And so working back towards the source. Now these resistors are in what with each other? Parallel. Can I do product over sum? Yeah. Okay. You know, before I go plug in and chug in, let's get an estimate real fast. If it took this guy 9 hours to paint a fence, takes his friend 15 hours to paint the same fence. They work together. How long do you think together? Maybe about, I'm gonna guess about 6 hours or so, something like that. Yeah, plus or minus a little bit. Okay. So hopefully I should get about that many ohms. Let's see if it's true. Because this is total is product over sum. The different context, think about that. Okay. Okay. Yeah, that was pretty close. Right. Like this number looks reasonable. Like this many ohms. Okay, that's way too precise, but you guys get the idea. About 5.6 ohms. Right? Yeah. I do see about 5.6 ohms on my answer choices. Yeah, see right there. All right, everybody right? Is right? All right, one more from the top half. Ooh, this looking guy right here. So. Okay, so this is this many ohms, uh, this many ohms, this many ohms, this many ohms. All right, so there's the circuit. Okay. So voltage source right there, fly over to the opposite side of the circuit, work my way back towards the source. Looks like these two are in what with each other, series or parallel? Parallel. So that's product over sum. All right, so product over sum, number of ohms. Let's grab a number for this. Okay, got an equivalent resistance right there. Redraw the circuit. Work your way back towards the source, and now those three resistors are in what with each other? Series. Yeah. So I can just add them up. Number of ohms. Is that? I think it should be about like that right there. Okay. Say, do I see an answer choice? Yep. Right. Boom. Right there. Okay. Okay. Is everybody okay? You guys all keeping up? Okay. So, if you keep it up with me, you should have the whole top half of that paper finished right now. You guys got that? We good? We good? All right. Okay, let's see the bottom half. At least well, I don't know if we'll do all these, but we'll do some of them. Okay. Okay, now, the bottom half of this page, there's actually a pair of questions for each circuit. One question is what's the equivalent resistance, which is what we've been doing anyway. Okay. But the follow-up question says, if I give you the voltage, like some voltage right here, can you solve for the equivalent current leaving the battery in amps? Okay, so there's two questions per circuit. Okay. And number 9, number 10 here, this circuit. So number 9, number 10. This one is unique among all the circuits on this page. There's something different about this. Draw this right here. Make this big. All right, so I got voltage source. Okay, now I'm gonna throw my numbers on the board. I got that. I got that many ohms. I got that many ohms right there. I've got that many ohms right there. And then I got a wire right down the middle right there. Okay. All right. Yes, who can tell me what's different about this one compared to all the other circuits on this page? Exactly. Yeah. Evan's got it. Yeah. This wire run down the center. Right. It has a name. Starts with an SH. It's called a what? I call it short. Yeah, it's called a short. And write down short right here. Okay. It shorts out. Because which one does it short out? Which if these were all light bulbs, if these were 4 light bulbs, which light bulbs would not even turn on? Yeah, these two right here are not even part of the circuit. You guys see that that's your entire circuit right there? That's your entire circuit. Yeah. Okay. Let's do a traffic analogy. If there was a line of cars, suppose there's like 100 cars of traffic and they're driving around town, got to get back to that parking garage, which is the voltage source. Okay. They hit this junction. Okay. You look to the left, you see like 9 stoplights. Okay, yeah. You look to the right, you see, whoa, there's 0 resistance at all. There's no stoplights, big old wide super highway. Right? Yeah, it isn't the entire 100% stream of traffic going to go along that road. Yeah, because it's the path of 0 resistance. Usually path of least resistance, but in that case, 0 resistance. Yeah. So these two aren't even part of the circuit. There's your entire circuit. Right. And since that's your entire circuit, oh, well, now those 2 resistors are in what? Series or parallel? Series. So can you just very simply add this? That plus that equals that. That many. Okay. I think that should be the total resistance right there. Boing. Yep, got that. All right, are we good? We're good. Okay. And then the follow-up question, number 10. Number 10. Let's go over to Ohm's law. Do you guys remember Ohm's law? Current is voltage on resistance. Or a lot of textbooks might throw a delta V right there, like a potential difference. All right. Anyway, I did give everybody 5 volts. I gave everybody 5 volts. And take your answer from number 9, because that circuit we just saw. However many ohms. Wouldn't that right there represent the current in amps? Okay. And you guys can use your own numbers. So take 5 volts, because you have a 5-volt battery also. I count however many ohms. Okay. So I have this many amps leaving my battery. Right. And since it's series, then I know that many amps also go through the 2 resistors that matter. Right. And here's my answer choice. Boing. I'll get right there. All right, guys good? Everybody know where we're at? We're all right. Okay. All right, guys ready for next circuit? Next circuit. Let's do right beneath it. Number 11, number 12. Ooh, this one looks fancy. 11 and 12 right here. Okay. All right, so I got this many ohms here. This many right here. This many here. This many ohms here. And this many ohms here. All right, you guys got your circuit drawn? Okay, so find your voltage source on the left side, fly over to the opposite side of the circuit, work back towards the source. Okay. And first 2 resistors, these 2, guys, these 2 are in what? Series or parallel? Series, yeah. Whatever current happens to have made its way to that part of the circuit does have to go through each one sequentially. Okay, so can I just say this equals, just add them together? Is that okay? Add them together? Okay. All right, redraw the circuit. Redraw the circuit. Draw an equivalent circuit. We'll let you get voltage on this. Alright, this many ohms, this many ohms, this many ohms, this many ohms. Alright, that could be an equivalent circuit right there, right? Okay. Alright, everybody good? Alright, so working back towards the source, now we run into this resistor. Now these resistors are on what? Series or parallel? Parallel. Okay. You know it's parallel because whatever current's making its way to this part of the circuit is going to hit this junction, and isn't that current going to split? Current's going to split. Ooh, definitely parallel. So add them together or treat it like two guys painting a fence. Two guys painting a fence. Let's do product over sum. Product over sum. Number of ohms. So we got here. Looking at that many ohms right there on my paper. All right. Let's draw the circuit again. All right. Okay, work back towards the source. Okay. Ooh, now those three resistors are what? Series or parallel? Series. So can you add those together? 6, 7, 8, 9, 10, 11, 12. I think if I add them together, you're getting that number right there. Point. It's like that. Okay. So is that an answer choice? Yeah, right here. Okay, that's an answer choice. Okay. You guys also getting an answer choice to number 11? Are we good? Okay. All right. The follow-up question number 12 is what's the current? Number 12. So let's do Ohm's law. The current that flows is the voltage over the resistance. I did give everybody 5 volts. Got that. And the resistance is, well, whatever answer you just got for the total resistance. Okay. So this should be the current that originally leaves the battery. How many amps? I like that. Boom. Yep, that's an answer choice. All good. All right, guys, all right.
Okay, so if I took these three are in series. I took them and put them all together. So I could put part of my, this says.
Yeah, middle one's in parallel.
So if you add these together and compare them sequence, you can add them together in parallel. And then do the product for the sum to two parallel, they become one parallel.
Yeah, so series, parallel, and series. All right. Here, let's just like a big picture for these last few. Okay. So this one here, number 13, 14. Guys, these three resistors would all be in what? Series. And then you bring in this guy in the middle, it looks like R6, I labeled it. That would be in what? Parallel. Okay. And then you bring the last two in what? Series. Okay. How about let's do the very last one. You guys see 19, 20? Okay. So here's my voltage source on the left side, fly over to the right side. Looks like resistors 2 and 3 are in what with each other? Series. And then with R5, you bring it in what? Parallel. And then R1 and R4 would be in series, and then R6 would be in parallel. Okay, so that would be a process. Does everybody see that? Okay. All right. So let's skip those. Let's head over to the back side of this page. Okay. All right. So this starts out the same. Okay. But now we're going to dig into the circuit because all the questions you could ask what's the current across each individual resistor. You could ask what's the voltage drop across each resistor. You could ask what's the power in watts across each resistor. Those could all be questions. The nice thing about these Kirchhoff tables is that you answer all those questions just in a single table. So let's start off with the series setup, which I just showed you guys the waterfall model a few minutes ago, beginning of class. So if this was a stream of water rather than electricity, wouldn't the stream of water leave this pump and then have a short waterfall here that could maybe represent one of those resistors, and resistor C, and then this could be resistor B is that waterfall, and then resistor A is that waterfall. And then the stream, say the current, routes back to the battery, the pump battery. Okay, so that could be your waterfall model right there. Okay. Now, guys, the height of each waterfall represents what in electricity terms? Yeah, voltage. Yeah. Right. And that's one of the questions: is what is the voltage drop across each one of those resistors? Okay. Hey guys, what do you know the three voltages have to add up to? Yeah, whatever your battery is. Now, my battery happens to be 12 volts. Yours is however many volts. Okay, guys, yeah. Okay. All right, so just think ahead a little bit. Right. That would be Kirchhoff's loop rule, wouldn't it? Kirchhoff's loop rule. Okay. Let's try this. Since the three resistors are all in series, how do you find the equivalent resistance for the whole circuit? Add them up. So mine go 3, 2, and 1. So that would add up to 6 ohms. That's how many ohms. Everybody just add up their resistors. Right, on number 1. Okay. All right. Now, there's different ways to complete this Kirchhoff table. Okay. We got Ohm's law, of course. We got different versions of Joule's law. We've got resistors in series is going to be helpful. Resistors in parallel is going to be helpful. Okay. And here's Kirchhoff's rules and friends, because got loop rule, junction rule, and also all those other rules tell exactly how this current flow and voltage drop in different scenarios. Guess that? Okay. And so there's different ways to finish out this table. I think I'll walk you guys through what I think is the easiest way, which is let's finish off what's going on at the point of the battery. Because I know I have a how many volts battery going across how many total ohms. Couldn't I immediately at this point apply Ohm's law and solve for the current leaving the battery? Okay, guys, go do that right now. Do V over R. I have 12 volts on 6 ohms, which gives me 2 amps. Right, everybody figure out how many amps? Oh, I meant to give you guys a big hint on this side. Guys, on this side of the page, everybody has all whole numbers. You should not get any decimals at all. If you're getting any decimals, you missed something. Okay? Okay. So everybody's getting whole numbers. You guys got it? Everybody's getting whole numbers? Okay. Now let's go over to Joule's law. Now you can use different depending on exactly how the question is framed or what information you're given, any of these might be the most helpful. These tables, you can use P equals IV. Is that okay? So P equals IV, current times voltage. You have current, mine is 2 amps. You have voltage, mine's 12 volts. 2 times 12 is 24 watts, leave the battery. Okay. Right, so does everybody have at the point of the battery, that entire row filled? Yeah, shit. So the resistance, just add up the resistors because they're in series. Current is voltage over resistance. 12 on 6 is 2. That'd be amps. Power in watts, well, that could be current times voltage. 2 times 12 is 24. That's where my numbers are coming from. All right, you guys good there? Good? All right. Now, again, multiple ways to finish this table off. I know for, guys, resistors in series, what is always the same for resistors in series? The voltages or the current? The current, guys, the current's the same everywhere. The voltage drops might be different. In fact, they will be different if they're different resistors. Okay? But the current has to be the same. That's like saying the gallons per minute flow rate is the same through all those waterfalls. Okay? And you know what the current leaving the battery is. It's this number right here. For me, it's 2 amps. So since I have 2 amps leaving the battery, isn't it 2 amps through every single resistor on my circuit? Okay. Now, if you have 5 amps, it's 5 amps all the way down. If you have 7 amps, it's 7 amps all the way down. You guys get that? Okay, good. It's the same current everywhere because they're all in series. Now, it's not necessarily true on the other models, but that's true on this one. Okay? Is that okay? Okay. Guys, stop me if you have any questions. Okay. Can I apply a different version of Ohm's law? Let me give you guys a non-fraction form. Can I say the voltage drop could be current times resistance? When I say voltage drop, again, more like a delta V is what that is. Okay. So what is the delta V across any resistor? Well, I know for mine it's always 2 amps, but I have different resistors. Ooh, like I have this many ohms on one. That'll give me 6 volts. That could be right. Right. So that could go there. Okay. You just multiply these two. 2 times 3 is 6. 2 times 2 is 4. 2 times 1 is 2. Is that mature? Is that okay? All right, everybody getting whole numbers? Everybody's got numbers and they're all whole numbers, is that right? Okay. Now, let's check Kirchhoff's loop rule right here. Because my voltage drops are 6, 4, and 2 volts. So that's like 6 volts here, 4 volts here, and 2 volts here. Guys, what does that add up to? What is 6 plus 4 plus 2? 12, which happens to be the voltage from my battery. You guys see my battery is 12 volts? Okay. Because if you're on track, if you're doing everything right, then your individual voltage drops should add up to your battery voltage. That's Kirchhoff's loop rule. Is that also working out? Okay, it's working. You guys good? Okay. All right, you guys ready to figure out power in watts? Okay. So let's do power could be current times voltage. Okay. Power is current times voltage. So just take these last two columns. So 6 times 2, I have 12 watts here. 4 times 2, that's 8 watts here. 2 times 2, that's 4 watts here. Okay. All right. Hey, everybody doing all right? Everybody doing all right? Guys good? Okay. So you should have the whole table filled out. Let's do a final check. And guys, the final check goes like this. Do you guys think that electricity supply has to match electricity demand? Supply and demand kind of thing? Right. So if you add up all the number of watts demanded by each of the resistors, let's do that right here. So guys, what's 12 plus 8? 20 plus 4? 24. Aren't my 3 resistors demanding 24 watts of power? And how many watts are exactly supplied by the battery? 24. Okay. Now, of course, you guys have different numbers than I do, but that should still be the case that if you add up all the power demanded, it should be exactly supplied by the battery. Okay. Is that working out for you guys too? Working out? Okay. Okay. All right. You guys ready for the next one? Okay. Okay. What's that? Oh, yeah. Thank you. I almost forgot that. Guys, the brightest bulb on the circuit. Which property would indicate the brightest bulb? That'd be the one with the greatest number of watts, greatest power watts. Right. So if I have a 12 watt is my greatest number of watts, I'll circle. Yeah, that'd be the brightest bulb. Right. Because the brightest bulb is the one with the greatest power in watts. Yeah. In this case, it's all in series. I think yeah. All right. All right, let's skip over to number 4 because I think it's the next easiest one to figure out. Number 4. Guys, these 3 resistors are all in what with each other? Parallel. Right? Now I gave you the resistors and of course the battery voltage because I did that for all these. Right? And everything else is determinable. Ooh, should I treat this like 3 guys painting a fence? Right? Now I could do product over sum, but I could only do that for 2 at a time and then have to draw an equivalent circuit and then bring the third one later. Or I could go back to my fraction method. I'm going to try that. I'm going to try my fraction method. No matter how you do it, you should get the same answer at the end. I think this process is just a little faster with the fractions for this one. So that plus that plus that. Notice I'm adding reciprocals. Okay. Reciprocals. Okay. Add those reciprocals together. I'll let the calculator crunch those numbers. That plus that plus that. Okay. Oops. Okay. And then so that's 1 over the answer is this many 1 over ohms. Okay. But there's still a set left. Guys, I still have to take the what? The reciprocal. Let me try that. See, I was talking right above the 7. Oh, do it for me. So the total resistance then is, I'm getting this many ohms. All right. Are you guys also getting a total resistance in ohms? You guys good? You're good? All right. You should be getting a whole number. Guys, again, there's no decimals. If you got a decimal, go back and do it again. Okay? Right, so you should be getting no decimals here. These are all whole numbers. Everybody getting all whole numbers. All right, let's finish off this row at the point of the battery. Let's do Ohm's law. I have this many volts on this many ohms of resistance. Would that work out to this many amps of current? I equals V over R? Does everybody have their current? Everybody has their current. Right? I equals V over R. 12 over 2 is 6, right? And let's do power in watts. Let's do Joule's law. Can you go P equals IV? 6 times 12, 72 watts. That here? Right? So, all right, guys, is there any question how to figure out that row? Any question at all?
Sorry, can you repeat that one more time?
Yeah. So, I applied Ohm's law. I got the current, do voltage over resistance. I gave everybody the voltage, right? And you just found the resistance. Are you good with the resistance? Got that?
Yeah.
Right. So for me, that'd be 12 divided by 2. That's how I got the 6 amps. Okay. Right. Now, after that, I flip over to Joule's law. Now, I can use any of these. They'll all tell me the same number. But I can go current times voltage, for example. And that'd be 6 amps times 12 volts is 72 watts. Okay. right, everybody's getting all these, and they're all whole numbers. No decimals. Okay, everybody right? Right. Now, guys, for 3 resistors in parallel, all those have to have the same what? Voltage or current? Voltage, right. Now they would have the same current if they're all the same resistors, but that's probably not the case. But they have to have the same voltage. They have to have the same voltage. Here, you get it really stands out on the waterfall model. So if I have 3 side-by-side waterfalls, right? You might have a skinny waterfall and a fat waterfall, which would represent different currents, but they all have to have the same height drop because they're all falling off the same cliff in this case. You guys see that too? Right? So it in that height drop matches the height of the battery or the pump that pumped them up in the first place. Is that? So the fact that I gave you how many volts is the battery, doesn't that voltage exactly apply across every single resistor? You can just copy paste that entire column right there because they're all in parallel. Okay. Okay. Let me find Kirchhoff's rules. We could have actually used this to check the original table we did too, where they were all in series, but here they're all in parallel, right? And here in series, this was the rule that we used, and in parallel, we can use this rule. Right? Voltage drops the same everywhere. Can you guys use Ohm's law to figure out the current now? I equals V over R. So take this V divided by this R, gives me the current in amps. V over R, V over R. Right. So you should have just filled out the current in amps. Just do I equals V over R. That's Ohm's law. So you guys just do Ohm's law, I equals V over R. Right, everybody good? Everybody's getting whole numbers? Okay. Now guys, look what the current added up to. Because the current leaving my battery is 6 amps. Then it splits 3 ways. But you guys see if you add up those split currents, in my case 4 amps, 1 amp, and 1 amp, it adds up to the original 6 amps. That's the junction rule. That's the junction rule, isn't it? Okay. If 6 cars leave this garage, if 4 cars down the street, 1 car down the street, 1 car is down the street, now I've accounted for all the cars that are driving around town. Right? Because cars are kind of like amps. Right. Okay. Power in watts. Can you guys do P equals IV? Power is current times voltage. So this current times this voltage, 4 times 12 is 48 watts. P equals IV. P equals IV. Right, I just did power is current times voltage. Knocked all those out. You guys do power is current times voltage. I just did Joule's law right there. P equals IV. Just did that. Any of those really will work. Okay. You do any of those, they'll all tell you. Okay. Let's do a final check. So, does power supply match power demand? So what is the power supplied? Well, that's in my case 72 watts. That's from the battery. What's the power demanded? I have to add up these 3 powers. So that many watts plus that many watts plus that many watts. Oh yeah, it's a match. It's a match. You see, it's a match right there. That's everybody right? All right. You guys good? Everybody's good. Everybody's good. Okay. By the way, again, you could let me do a review for this one, and I'll go back to the first one again because I want you guys how this also maps to these Kirchhoff rules. Okay. Do you guys see this very last rule I have that falls out? It says how the current splits based on resistances. So it's like a path of least resistance thing. The more resistance that resistor B is, the more current goes through a branch A, right? That's a branch. Okay. Do you guys see at a glance, like if you have different resistors, your smallest resistor should have the greatest current going through it? That's also true? See, you could have used this rule and solved it that way too. It would have been a little bit more difficult to navigate the table that way, but you could have done that. Okay. Okay. Maybe draw an equivalent circuit and blah, blah, blah. Okay. Or if I go back to number 1, where these were all in series, you could have, instead of finding current first and using Ohm's law to find the voltage drop, you could have jumped straight to finding the voltage drop first by applying this rule, where the voltage drop is proportional to each resistor. You guys see on number 1, if you have a largest resistor, it also has the largest voltage drop. Right? That's what this rule says right here. Okay, so you could have done this first and then use Ohm's law to find the current, and lo and behold, all the currents would be the same because they're all in series anyway. Okay, you guys good? Good? Guys good? Okay. All right. Oh, let's do number 3. Number 3. Now, number 3, you guys see these 3 resistors are in what? Series. Let's add those together. That's resistors A, B, and C. So 3, 4, 5, 6. Right. And then that's in what with this last guy? Parallel. So I have 6 sums there because 3 plus 2 plus 1 is 6. And then bring in this 3. So I'll do product over sum. So I'm going to do 6 times 3 over 6 plus 3. Right. I'm getting a total equivalent resistance of this many ohms. Okay. Right. Guys, go ahead and do that. It's like we did on the front of the page. So add up resistors A, B, and C because they're in series. Write that number down. And then bring in a parallel with resistor D, which is at the top of the table. Do product over sum. Now, if you did it right, you should be getting a whole number. You should only be getting whole numbers on these tables. Okay? All right? All right, let's finish off this row. Can you guys go? Current is voltage over resistance. Right, that'd be this many amps. You guys do power is current and voltage. Right, that'd be this many watts. Right, guys see this? See that? Right. All right. Here. See what you guys want to do. Let's do a vote. Guys, tomorrow we can take another day to do more circuits. If you guys want to do more circuits, or we can close this down right now and we can go on to FRQs tomorrow. Right, guys, let's do a vote. How many guys want to do take another day to do more circuits? Who wants to take another day to do more circuits? Got 1, 2. Right. Who wants to do FRQs starting tomorrow? FRQs. Ooh, that's easily most of the class. All right, so let's go ahead and cancel the rest of these. So scratch off number 3. I'm not going to grade number 2 or 3. I'm not going to grade those. And I'm also not going to grade these two. Here, the only ones I'm going to grade are the ones that we did in class. Now, if you've been following along in class, you feel good about what you have, then turn this into the grade tray. If you think you missed something, you can turn this in later this week. That's okay too. Okay. Right. So I'm only going to grade the ones we did in class. You guys got that? I'm just grading the ones we did in class. So these 2 Kirchhoff tables, number 1, number 4. Right. And on the front, well, just the ones we did in class. Right. Yeah.
Here.
Oh.
Yes.
Okay. Here you go. Right, see this online.
Yeah.
All right. Yeah, you guys have a good day.